Logarithmic moves and we know what they do to the graph. If you know the graph of f of x, and you add a constant c inside of the parentheses of that function, what does that do to the graph? Goes left by c. What if you add that constant outside of the parentheses? Up by c. If you make the whole function negative, Gesundheit. So it'll flip it over which axis? Over the x-axis. You'll do the flip that changes y values. And sometimes it's safer to say, do the flip that changes y values than flip over the x-axis, because that's really easy to accidentally missay. Flip over x-axis. Do the flip that changes y values. What about f of negative x? I'll do the other flip, right? Instead, yeah. Cool. And once we have all these things, we can put them all together. So let's try to do that. So let's try to sketch the graph of negative x plus 3 quantity squared plus 4. Seem easy enough? Let's do that. We know what the graph of f of x equals x squared looks like. So let's go ahead and start there. Start with the graph of y equals x squared. And again, when you're graphing by hand, it doesn't need to be perfect, but it does kind of need to look roughly right. And there's an order that I'll deal with these symbols. Maybe we'll talk a little bit about what happens if you do these in the wrong order. First, I'll deal with the negative sign. What happens when you put a negative sign in front of that x squared? Flip it over the x-axis. All right, let's put that plus 3 next to the x. What does that do to the graph? Moves a 3 to the left. So I guess this point 0, 0 will now be a negative 3, 0. And I don't know, what do you think? Is it worth tracking exactly where the y-intercept is at this stage? We could, but this isn't the final answer anyway, so maybe I'll just have that picture. What should I do next? What will the plus 4 do? Move it 4 up. So this vortex point will now be at negative 3. It'll be generally downward trending. And I've only drawn that much of it because I want to have the right intercepts. Does this problem ask for the right intercepts? I don't think it does. There would be a few homework problems where, I'll demand the right intercepts. How do you find the precise value of the x and y intercepts? I guess y-intercept first. Plug in 0 for x. Let's do that. And I don't know, I could do, or I could just pause and let you do. And maybe I'll do that instead. Do some work. Tell me, what is the y value of the y-intercept of this graph? What'd you get? -5. right, so the y-intercept is at 0, -5. I guess that tells us two things automatically. I know there will be an x-intercept somewhere in this range, because it has to get to this negative value. And because of symmetry, there should be one over there, too. Let's find the x-intercepts, though. And maybe I'll give the same options. Should I do any of the walk involving finding these x-intercepts? Cool. Then I'll be quiet for a second. You'll tell me where are the x-intercepts. I think intuitively I figure like it seems like there should be two of them, right? Because the parabolas are going to calm down and hit again the x-axis. Where are the two x-intercepts? You got -6, -1. Those agree? Right here, I'll call for -5 instead of the -6. Cool. And I haven't like checked these. -5, -1. -6, -1. Cool. I think that's enough time for us to go through it. So let's go through and do this. So I guess you have to solve -x plus 3, then you square it, then you add 4 equals 0. What seems like a good far step? Move the 4. Why not? -x plus 3 squared equals -4. What seems like a good next step? Well, the left and right hand side are negative, right? So maybe we'll just cancel those negative signs. All right, what next? Take the square root of both sides, and I'll do something slightly wrong, and since there's what am I missing? Yeah, whenever you cancel a square by using a square root, you lose positivity and negativity information. Right? There are two things whose square is 4. There's 2, and the square root tells you that, and then there's also -2. So +2 or -2, and what next? Oh, yeah, sure. So there are two different equations now. X plus 3 equals 2, or x plus 3 equals -2. And each of those you can just subtract 3. X equals 2 minus 3 is -1. Good, that one checks out. X equals -2 minus another 3 is -5. So I think I agree with the -5. Looks feel okay? All right, let's plot these. So there's one at negative 1, 0. There's another point at negative 6, 0. And I know that this graph has to go through those points. And otherwise it should look square, like a square. Whoop. Yeah.
Did you just say it was negative 5, 0?
Yeah. Yeah, I didn't I? And it is negative 5, 0, right? That was actually correct. Cool. Folks feel pretty good? So, I think I'd like to take a moment, and well, maybe I'll see how you all feel. I'm definitely going to have you all do at least one more example on your own, as I still demand that I talk through one more example of just graphing by transformations. All right. Then, I think I'm going to have everyone do the same. Would you rather do the one involving the absolute value, or the one involving that square root? I think I saw like half a vote either way. So this one's got more minus sense. Do the square root one. All right, so multiple choice question with 16 options. Because of technology constraints on the final exam, all multiple choice things will be limited to at most 5 options. On some of the quizzes or midterms, I might do bananas things like this. But for now, let's read it. So, or maybe on none of the above. Did anyone wind up with a graph not in this list? Cool. Then let's see a show of hands. A? Half will vote for A. B? Vote for B. C? D? Vote for D. E? F? You know what, how about, let's do it this way. This vortex point at -3, +3, -1. Some of those. Vortex at -3, +1. Maybe that's the most popular one. Vortex at -3, -1. All right, so lots of controversy. And let's start with this. This is just going to be like a good aside from multiple choice test taking strategy. What's something you could do to check that doesn't have to do with graphing by transformations? Let's check if this was the most popular one, right? Let's see if when you plug in x equals -3, you get a y value of 1. Let's just do that to check. Plug in x equals -3. We will get y equals negative the square root of -3 plus 3 plus 1. What's that wind up being? I think +1, right? Because that's a +1 at the end. Should it be a +1 at the end? All right, -3 is +3. Oh, no, that's bad. +3 plus an extra 3 is +6. So it would be negative the square root of 6 plus 1. Square root of 6 is like somewhere between 2 and 3. 3 point something. Those of you with a calculator can give me more digits, but I don't think I care. So here's the point. When I plugged in x equals -3, I got something bigger than 3. -2. Oh, because I lost this negative sign, didn't I? Yeah. So let's see, that -6 on its own is -2 point something. So I think the whole thing will be -1 point something. Okay, good save. But here's the point. Could this possibly be right then? Since this is exactly at a y value of -1, could any of these be right? And could we eliminate a bunch of other ones that don't appear to have a negative y value when x is -3? Yeah, so that helps. Let's actually go through the process of walking it out correctly, because I think it'll be worthwhile. Because there is a subtlety that this is bringing up about the order in which you do these moves. If these things happen in the wrong order, then things just won't work out correctly. So, let's see. We started with y equals root x. What was the first move that you did? Think about negative root x. What does that do to the graph? Yeah. Right, it's easier to describe in a hand motion. And if you do that, I know that you know what you mean. What next? Yeah, let's add the 3. And you know what? Let's also do the +1 in the same step. Because Those are both just be shifts. So let's go next square root of x plus 2 plus 1. So I guess this will be left 3 plus 1 up 1. Left 3, 1, 2, 3, up 1. Something like that. All right. And what's the only thing left that I need to deal with? Negative in front of the x. So negative square root of, maybe just for emphasis, I'll put this negative sign in red. Negative x plus 3 plus 1. What will that do to the graph? Flip it over the y-axis. So let's pay attention to this point. This point right now is at negative 3, comma 1. Where will it go into this transformation? Positive 3, comma 1. So this point will wind up over here at positive 3, comma 1. And then it should look downward opening square root-ish. Cool. How many people dealt with some of these things in a different order? Let's see what happens if you do. What order did you do?
I did the negative before.
All right, let's do that. Square root of negative x. That'll reflect it over on the y-axis right now. And the reason I want to emphasize this is because I want to explain why there is this subtlety. And after we see that there is this subtlety, we'll just write down the order that you should do these moves. What did you do next?
That was the second to last before I did the transformation. So like I put the negative in front of the square root sign. And I put the negative.
Oh, okay, yeah. Did both of them at once? Okay. Cool. So at this point you are there-ish. So let's see what that would do. So that'll be negative the square root of negative. And so when you do this shift left by 3, you add 3 to the x. So you're adding 3 just to the x, so the parentheses show up like that. And then you add 1 to the whole thing. What does that result in? You now go left by 3, because of this plus 3, and up by 1, and otherwise the graph looks something like that. Nice. So let's focus inside of the square root with those parentheses. And probably when you wrote it the first time, you didn't have those parentheses. But it matters because when you do the horizontal shift, that corresponds to adding things to the x, not to negative x. So your really graph looks like it's the square root of negative square root of negative x minus 3 plus 1. So if you accidentally do these moves in the wrong order, you might wind up with some distribution errors. So I think I just want to say one thing before moving on to the next idea, which is going to be the last of the transformations that we'll build, is the order in which you should deal with these things. So whenever you see plus or minus plus or minus x plus c plus d, here's an order that you should deal with these things in. Deal with that plus or minus sign in front of the whole function first. Then do the shifts. And then deal with this plus or minus sign last. And when in doubt, if you find that this is a particular detail you struggle with when you're doing things like the homeworks, remember that there are things you can do to double check. Right, like you can plug in a point that you know should be on the graph that you just generated. And if it's not, then probably you did one of these and not the right order. And once you do that, you can figure out where this ordering error happened by being very careful with your parentheses and saying exactly what you graphed at each stage. And in fact, the order is not even so picky as this. As long as you deal with this before that and this before that, it's fine. But this is one particular way of doing it. So, now that we've done that, what's another thing you could possibly do, say on the homework, to double check that you have a graph correct? Yeah, and like use a computer to graph it. Right, like there's value in doing things by hand, but a computer can also do it by just evaluating at 1 billion inputs. So, there's this Desmos generated graph. Does that agree with the one we decided looked right? Nice. And this ordering issue really is the subtle point. So, let's introduce one last type of transformation. So far we can deal with the case that you have like plus or minus signs in those two spots I underlined in yellow. Do you think we could also figure out what happens if there's like a 7 in one of those pink blanks and a 2 in the other one? That also seemed like something we should be able to make sense of. I bet. And you know what? Let's try to figure it out, in fact, by doing like a computer-based graphing. So let's take this function. Here's the function f of x equals 1 minus absolute x minus 1. And it doesn't matter that that's what the function is. Let's play with Desmos and graph it. So let's start with f of x equals 1 minus absolute x minus 1. Is that something that we could have graphed by hand? Yeah, I think so. Like it's some shifting and some flipping. But that's not the point of right now. Let's look at that and see how the graphs of f of 2 times x and 2 times f of x look. And maybe let's start with this because doing things outside of the parentheses usually behaves the most intuitively. So going from the red graph to the blue graph, what looks like happens? It narrows? Sure. That's true. I'd want to use a different one, yeah. X-intercepts remain the same. That's good. What happens to the y values in general? Yeah. Compresses. Kind of, like it is looking kind of narrower. But think about what's happening to the y values here. Yeah.
Y values are doubled.
Y values are getting doubled. So yeah, it is kind of compressing in a way, but it's also just stretching vertically. All the y values are being doubled. So, let's write that down. So to go from the graph of y equals f of x to y equals 2 times f of x, it looks like all the y values double. Which I would want to describe as like a vertical stretch by a factor of 2. And I feel like every time I give this lecture, because I teach this class with some frequency, when I get to this point, I'm always super uncomfortable with how do you spell stretch. Is that right? Okay. Okay. Thank you. It seems like that T shouldn't be there. Maybe there should be an extra A. But if you say it's right, it's right. Let's think about the other one. Y equals f of 2 times x. So if multiplying the output by 2, that doubles all the y values. And maybe that makes good sense. You double all the output values of the function. That's what multiplying by 2 means. So yeah, that should be a vertical stretch. What do you think should happen before I even graph it? What do you feel like should happen when I multiply the inputs by 2? Yeah, it should be like the opposite, and it should be horizontal. So I think a compression will happen, and it'll happen to the x values. I think the x values will get divided by 2. And let's see if that happens. F of 2 times x. Turn off this graph. Does that look right? Going from red to green, does it look like all the x values on the graph have been halved? Yeah, cool. So to go from the graph of f of x to f of 2 times x, it looks like all the x values on the graph get divided by 2. And there's one handy thing you can do in something like Desmos. You can create these little sliders. And let's just see what happens if you replace that 2 with a different scaling factor. So let's just see what happens as this value changes. As that constant c goes up, does the x value get divided by just bigger and bigger numbers? All right. As the c value started at 2. As the c value goes down to 1, well, multiplication by 1 obviously does nothing. When you multiply by small things, the x values get the opposite effect. They get bigger. Cool. And then I guess like you can just let the video play, right? That seem reasonable? Nice. Let's see if the same sort of thing happens with 2 times f of x. Oh, c times f of x. For various c values, is there a vertical stretch depending on how big that c is? Looks like. And when c is negative, it flips. But you already knew that because you knew what a negative and vertical function should do. So those are the last of the moves we have. And like, it's nice to have that, but it gets hypnotic. So for any constant, for now I'll say positive, if you know what the graph of y equals f of x looks like, then you can get the graph of y equals c times f of x by, maybe I'll say this 2 different ways, multiplying all y values by c, or stretching by a factor of c. If you want the graph of f of c times x, you will divide all x values by c, or you will compress horizontally by a factor of c. And hopefully that agrees with what the previous page said, and what the little Desmos interacted with. Nice. So, let's play this game. I don't need to scroll this way. There's an order issue that we saw last time. In general, deal with whatever you see multiplied by the whole function. It might be positive or negative, and then some number. Do that first. Then do your shifts. Finally, do whatever horizontal scaling and flipping maybe should happen. And let's now just play this game. Here is a thing to graph. Let's try to graph it. And, well, let's talk it through. According to these rules, which of those symbols should I deal with first? negative in front of the square. So maybe I'll even have a step right here where I say here's the graph of y equals x squared. First thing to deal with is this negative sign, negative x squared. Okay, what should I do next? Yeah, we'll do the 2 and the 3, and the specific transformation those do is they do shifting, right? So I should shift it right 2 up 3. So right by 2, up by 3. 1, 2, 3. 2, 3. And then it'll look parabola-y. And I'm only going to draw it that far because I don't want to make sure that I have the right x and y intercepts right now. Because I'm not done anyway. What should I do next? Well, what's the last item I have to deal with? The 1/2. And let's deal with this 1/2. So this was the graph of y equals negative x minus 2 squared plus 3. Let's think about what that 1/2 will do. Well, let's read it out right here. This will divide all x values by 1/2. And maybe one way of writing that is each new x value will be an old x value divided by 1/2. And maybe I'm beating a dead horse a little bit. But like, now that I've written it that way, it's more explicit because what does dividing by 1/2 do when you, I guess, simplify? Yeah, just say it loud. It multiplies by 2. So what will this do? This will take all x values and it will multiply them by 2. So this 0.23 is the only labeled x value right now. Where will that point go? If you double that x value, you get 4. Y value stays the same. So there will be a point over here now at 4, 3. And then it'll look like a stretched out parabola. Should we be careful to get the right intercepts now? Right now we have the actual final function, so we may as well. Maybe I'll just be careful with my y-intercept, because that's the one that's easy to find. What is the y-intercept of this graph? I think it's -1, but I want you to like confirm. People agree? Awesome. So, I know the y-intercept should be at 0, -1, and it should look parabola-y. Cool. How do folks feel right now? That go okay? And now let's play a multiple choice game. Let's suppose that you did all that walk, and the problem just asks which of these 3 functions might be the graph of f of x equal to -1/2 x minus 2 quantity squared plus 3. And those were the options. Maybe I'll give them letters. A, B, C. A, B, C. Unclear. Cool. So we have an answer. Let's pay attention to this point. It looks like the point 4, 3 should be on the graph. 1, 2, 3, 4. 1, 2, 3. Yeah, that looks like the point 4, 3. So this one has the point 4, 3. 1, 2, 3, 4. 1, 2, 3. This one doesn't. That one definitely doesn't. So just by checking that vertex point, we have it down to just one option. Let's check the y-intercept also, since we computed that. What's the y value of the y-intercept of this one? -1. Not -1. It is -1, so it could be C by that standard. Cool. Any questions or subtleties people have on just this example? Cool. All right, and I have 5 minutes left. I think that is enough time to combine this with another thing that we've also already done. So now we have more functions we can graph. Anything that starts with an elementary function that you do some transformations to, we can graph it. But that means that each of these ingredients are things we can graph. Whenever we have a bunch of ingredients that are all things we can graph the piecewise function. So let's try this. Let's sketch the graph of f of x equals x minus 1 if x is less than 2, x minus 1 quantity squared if x is between 2 and 3, and just 3 if 3 is less than or equal to x. And let's just do them one at a time. Y equals x minus 1. Tell me what that graph looks like. Let's see, it's a linear function, so the graph will be a line. That line will have slope. Yeah, but say it. 1, yeah. This is a line, slope 1. Where is its y-intercept? -1. Or 0, -1, depending on how pedantic you want to be. And let's also emphasize the x values that you care about that. So I care about that for everything less than 2. Let's see, that point is at 2, 1, I guess. So for the final graph, I'll see this point at 2, 1, and to the left of that, I see a line of slope 1. So far, so good? Let's think about x minus 1 squared. What does the graph of that look like? Let's see, it'll be a parabola, right? It'll look like y equals x squared, but then shifted a little bit. Right one. So I guess that means I'll see this point 0, 1. Graph will look something like that, but I only care about that between x equals 2 and x equals 3. 2 to 3, so let's just plug in those. So this point will be 2, 1. Plug in x equals 2 to that, I think you get 1. Did I screw up yet? Is that right? Cool. And 3. So let's emphasize that. When you plug in 3 to this formula, you'll get 3 minus 1 is 2. Square it, you get 4. 3, 4. Let's see, I guess this one should be an open circle, that one a solid dot. So, starting at 2, 1, then you'll see something parabola-y until it gets up to 3, 4. So far, so good. What does the graph of y equals 3 look like? Horizontal line, y equals 3. Right, there's nothing to describe it. It is the line y equals 3. So it looks like as soon as x is bigger than 3, or equal to 3, you will only see y values of 3. That feel pretty okay? Nice. And as a reminder, you have access to computer tools. If you graph a piecewise function, you can check if that graph is correct, maybe by looking at something like Desmos. Desmos is capable of graphing piecewise things. It isn't capable of really knowing what happens at the endpoints. In fact, no computer really will. A computer graphs by plugging in a bunch of inputs. That won't tell you what happens exactly on the nodes at any input, because it might not be a number that the computer tests. So, you can graph each piece using this sort of notation. Where you care about that formula, that's what the formula is. And you might be able to do that on your like graphing calculators too, but Desmos is just a better tool anyway. All right. And, oh, I'm even on time. All right. So as people are packing up, I know all the computer clocks are synced. They'll all be the same. And I'm pretty sure all of those are synced with each other. But the computer and that clock are not synced up. Which one does your next class use, if you have a class right after this?
My watch says 9:51, the computer says 9:51.
Oh yeah, the computer is right. I know that was wrong. But if your next class starts by that one, I should pay attention to it. It's too late to ask that now. Everyone's gone. Yeah.
So, I completely forgot that at the beginning because I was like trying to remember which one it was. But I don't know what else I'm missing.
Cool. Scroll up. There should be more numbers in your list. Okay. Let's see. So this is the list of max. Okay. Cool. And what's the list of local maximum?
Or the relative.
Yeah.
Are those
Well,
the
it's,
same?
yeah.
Oh, okay.
So that one clearly is a local max because you're looking at values and see things less than it. This also local max because you don't see anything nearby
Yeah.
that's bigger than it.
Should I have those two
I thought I fixed this. Oh, I thought I fixed this problem. Yeah, your answer is right. Your
Okay,
answer
so it
is
should just be
objectively
two?
There's only two. Send me an email because
You said shouldn't count.
endpoints never count. And in fact, check out those endpoints. Those are open source.
Yeah, that's nice.
You can't even evaluate.
Yeah.
So,
Alright, send you an email?
yeah, because, yeah. And say which problem it is because, not that I had fixed this problem, but.
Yeah.
So the issue is that there's like no two students will have the same exact problem.
Yeah.
And so it's designed with some randomness. And so I had to account for that randomness when I wrote the solution. And apparently I didn't do it right.
Okay.
Yeah.
Thank you.
Yeah, and you. All right. So, how are people feeling?
Amazing.
Well, that's good. Do you know what building just had that fire alarm? Okay. It was one of them, though, right? There was a beep coming from outside? Okay. Okay, I guess that makes sense. Yeah, that's all.